Recall that when we discussed strategies for integration, we said that not every function has an antiderivative that can be expressed in terms of elementary functions. And as an example, I gave you this antiderivative, e to the minus x squared dx, and I said this function that represents the antiderivative of e to the minus x squared cannot be expressed in terms of elementary functions such as polynomials, trig functions, and so on. Now, it is interesting though that this antiderivative can be expressed as a power series. Indeed, let us do just that. Let us denote this antiderivative by the uppercase f of x, like so. And let us obtain an expansion of this f of x into a power series. Specifically, we will obtain its Maclaurin series. So our goal here will be obtain the Maclaurin series for f of x. So the way to do it, of course, is to say, well, let's start with e to the minus x squared and express it by a Maclaurin series. So let lowercase f of x be e to the minus x squared, like so. So we know that e to the x is given by the following Maclaurin series: k from 0 to infinity, x to the k divided by k factorial. This is the representation of e to the x, which converges for all x. So it has radius of convergence equal to plus infinity. This means we can obtain an expansion for f of x, for the lowercase f of x, like so. We will simply take the expansion for e to the x and replace x with minus x squared in it, like so. Or if you simplify this expression here, you'll get the sum k from 0 to infinity minus 1 to the k, x to the 2k divided by k factorial. Great, so this is the power series for lowercase f of x. To obtain an expansion for the uppercase f, we have to integrate lowercase f with respect to x, like so, which gives the integral of the power series I have over here. And that would be k from 0 to infinity minus 1 to the k, x to the 2k over k factorial, integrated with respect to x. As we know by a theorem about integration and differentiation of power series, to integrate a power series, all we have to do is to integrate its terms one by one. So we'll have this integral here. I take minus 1 to the k outside of the integral because that's a constant. It does not depend on x. And here I must integrate a power function. So this gives me the sum minus 1 to the k times 1 over k factorial times x to the 2k plus 1 divided by 2k plus 1. And then I need to add a constant of integration, like so, to account for the fact that we are not using any initial condition here. And so the answer is that f of x, the integral of e to the minus x squared dx, is equal to the sum k from 0 to infinity minus 1 to the k times x to the 2k plus 1 divided by 2k plus 1 times k factorial plus a constant. And this is the answer. This is the antiderivative for the function that we started with. And so we have successfully expressed this antiderivative by power series. Finally, we should observe that this representation holds for all x. So indeed, you see that we started with a series that converges for all x's. Then we performed a substitution in it. We replaced x with x squared. So, sorry, that would be minus x squared. Which does not change the radius of convergence. And so the radius of convergence for the lowercase f is still plus infinity. And so once you integrate a power series that has infinite radius of convergence, you still get something that has infinite radius of convergence over here. And so this representation that we obtained holds for all values of x. In other words, the radius of convergence is still infinite. And so in this case, the ability to represent functions by power series gave us the additional flexibility which enabled us to express this antiderivative by power series.